Hello class, today we're going to be looking at heat transfer and chemical reactions. And so these are our 4 questions we're going to focus on. Distinguish between endothermic and exothermic reactions. Define activation energy. Explain how you could speed up a chemical reaction and how you could slow it down. Draw a chemical reaction graph. Label activation energy. Using different colors, show the difference with a catalyst and an inhibitor. Okay, so today we're going to be doing the notes for heat transfer and chemical reactions. You should be able to refer back to the labs that we were doing the day before. And if you haven't done those labs yet, you may be doing them after you hear these set of notes. And if you, by chance, were absent, you may be doing the virtual labs on these to show how heat transfers in a chemical reaction. So in a chemical reaction, we have heat either being absorbed or being released. And so we'll look at the different examples of that. An exothermic reaction should make you think of exiting. So thermic or thermal being heat, so exiting heat. And this is when heat is going to be released to the surroundings. So in this type of reaction, the temperature of the surroundings will rise because there's energy that's being released, so it gets warmer. This would be an example, or what it would look like if we are to show a graph. So we have our energy here is increasing, we have our reaction that's happening, so we have what we start with, reactants are at the beginning. We have our increasing energy as the reaction is happening, and then it releases all of this energy to the environment. So we see that our energy increases to a point where the reaction can take place, and then energy or heat is being released to the environment. Examples are hot packs. So if you have some of those chemical hot packs, you break the seal on the inside and then it heats up. Endothermic reaction is going to be the opposite of that. It's a chemical reaction that requires so much heat it actually pulls heat from the environment and makes the area around it colder. Sorry about that, I'll go too quick there. So the temperature of the surroundings will decrease because energy is needed. In this one, the graph will look a little different. It has maintained the amount of energy that it keeps in the product, so this is what you end up with. And in this one, our energy is still absorbed. It did not ever get released back to the environment. Now, it reached a certain point, which is called our activation energy. We're going to go over that in just a minute. But it never came back to its original level. So the reactants, how much energy was there, was much less, or had been much less than what the products have. The products have all of the energy. They've absorbed all the energy. An example for that would be a chemical cold pack, which many of you have probably used at some point in a first aid kit. So we need to go over some key words here. Activation energy is the amount of energy that's needed for the reaction to take place. If you never reach the activation energy, then the reaction cannot happen. So a simple, very simple example would be if I have a match sitting on a table next to a piece of paper, it will never light that piece of paper until I activate the match. And when I strike the match, that's the energy I'm adding to the system, and now there's a flame to that, and now I can burn the paper. So the activation energy is our total amount of energy that you have to bring to the system before the reaction will actually happen. And then we have 2 ways that we can either speed up or slow down the reaction. The first is a catalyst. It's also called an enzyme. Enzymes are catalysts, but catalysts include other things other than just enzymes. So a catalyst will speed up the reaction, and it helps to lower the activation energy. I'll show you this in a graph here in just a few minutes. So you reduce the total amount of energy that's needed for the reaction to take place, and it will speed up the reaction. An enzyme, just to clarify what that is, an enzyme is in living things. So it's a biological catalyst. And it would be something that we might have. We have lots of enzymes in our bodies, and it helps to make reactions happen faster. So here's an example of an enzyme. If you take in milk or a milk product, there's a milk sugar called lactose. If you have the enzyme lactase, you are able to break down that milk sugar. If you do not have the enzyme lactase, you will not be able to break down the milk sugar, and you will be lactose intolerant. So if you know anybody that is, that's what that means. They don't have enough of the enzyme lactase, or maybe none at all, that allows them to break down that milk sugar. And then opposite of a catalyst is an inhibitor. And an inhibitor will slow down the reaction. So let's say you really don't want the reaction to happen, you would do something that inhibits or slows down the reaction so that the reaction either doesn't happen at all or happens very slowly. So this is our general graph here. Activation energy is this highest point. It's the total amount of energy that you need for the reaction to happen. So you can see they've labeled it in here, and that's because we had to reach this amount of energy before this reaction could happen. Down here we have our reactants. These are the things that you start with, and we did that yesterday in notes. So that's the things that you begin any reaction with. And then these are our products, the things that you end the reaction with. This is a general chemical reaction graph. Now, if we want to show the enzyme and the inhibitor, we'll show first our catalyst. And in this one, you can see we have our reactants, we still have our products at the end, and we still have our activation energy. That's where we're supposed to reach in order for this reaction to happen. But we want this reaction to happen faster. So we add a catalyst, and what will happen is here in the green, we can see that the activation energy is lowered, and the reaction will happen much faster than it did without the catalyst. If we have an inhibitor, what will happen is this is our normal activation energy. That's where we would normally need that amount of energy here. But with an inhibitor, this is the amount of energy we need. We actually need quite a bit more energy for that reaction to take place. We are still starting at the same reactants, and we are still starting at the same products, but we're just making that reaction happen slower by adding an inhibitor. That's the end of these notes with heat transfer or heat exchange in a chemical reaction. Be sure that if you have not finished up the lab at this point, you would be able to maybe have more information to be able to finish those up. And if you were absent for the labs, you need to make sure that you're doing the virtual labs that are available.